Hey everyone, welcome back. So this video is going to be about model selection in time series. And what I mean by that is when you're building time series models, oftentimes there's several different models that you're considering. Maybe there's a AR model of a certain order, an AR model of a different order, an ARMA model with a certain P and Q, and you're not sure which is the model that you should use. In this video, we'll be looking at some real data. We'll be fitting a bunch of different models to that data, and we'll be looking at some considerations for how to figure out which model to use among several competing models that you've built. So the code and data that I'm using will be available in the description below. We go ahead and import a couple things, and the beginning part is just reading the data. I won't spend too much time on that, but we're using this catfish sales data that we've used in a previous video. So we go ahead and run a stationarity test, the augmented Dickey-Fuller test on this data, and we get a p-value of pretty much 0. So this data is stationary, and it looks like this, which does indeed look stationary. So this data ranges from 2004 until 2013. So for this video, let's stay simple, and let's assume that we're just going to fit an AR model to this data. The only question is which lag should we use in the AR model? We're going to use our old friend, the PACF, to help inform our decision. So here I have the PACF of the data you've seen above. And in many previous videos, I pretty much said something like, oh, it looks like it shuts off after lag 3, so let's just use lag 3, even though there were lags in the future that were significant. But in this video, we're going to be a lot more robust. We're going to not make any assumptions like that. We're going to say that obviously there are lags significant up to 10, and maybe even more based on how many lags I said I wanted. So we need to figure out which is the best AR model to use. So we'll be choosing between 4 AR models. An AR1, I chose that because the lag 1 is pretty strong and then it starts to kind of shut off for a while, so that's one candidate. An AR4, I chose that because lag 4 ends up being really strong again after 3 is kind of weak. An AR6, for the same reason, the 6 lag ends up being pretty strong over here. And an AR10, because even lag 10 is significant. So we'll be comparing an AR1, an AR4, an AR6, and an AR10. So the first thing we're going to do is fit each of these models to the same data that we have above. So that's what this code is doing down here. This code is basically looping over all of the different orders that I said I'm considering, 1, 4, 6, and 10. It is building a AR model of that order and fitting that model to the data. And then for each fitted model, we get the fitted values attribute from that object, which basically says, using that model, what would the fitted values on the data that we used look like? And we plot each of those below. So the data is in blue, and the fitted model is in orange. So an AR1 is the most simple of all 4 models we considered, and that has its perks, and we'll come back to that point in just a moment. But we can see that it's obviously not fitting the data very, very well. This orange trend does kind of fit the lows and highs, but it misses a lot. How does an AR4 do? A lot better. We see that it's matching the peaks a lot better than the AR1. What if we go to AR6? If we look closely, then we can see that it is doing a little bit better than the AR4. For example, here this jumps straight down, but here there's a little bit more signature of the data going on, and similarly in many other areas. So an AR6 seems to be doing better than an AR4. And if we look at an AR10, if you look really, really closely, you'll notice some differences, but the truth is that it doesn't look like it fits the data that much better than an AR6. So the big question is it worth those 4 extra parameters going from an AR6 to an AR10 if it's not fitting the data that much better? And to answer that objectively, you're going to be using 2 very, very popular metrics, not just in time series model selection, but in all model selection in statistics, AIC and BIC. Now, before we introduce the formulas for them, which are pretty simple, we need to introduce the components that are in those formulas. So the 3 components we'll be looking at are the log likelihood. So without getting too into the math, the log likelihood basically measures how strong the model is in fitting the data. And the general rule of thumb is going to be the more complicated the model, the better it fits the data. And that makes sense, right? If you add more parameters to a model, it can only fit the data better. But of course, that's not the only criteria we want to look at, because we also have this problem in stats that you've probably heard of called overfitting, which means that, of course, using a more complicated model is going to fit the training data better. But the more complicated you make your model, the worse it's going to be on the testing data. Basically, it matches the signature of the training data way too much and can't generalize to your testing data set. So for that reason, we also want to incorporate the number of parameters k in your model. So for our AR10 model, we have 10 parameters plus a constant. For our AR6, we have 6 parameters plus a constant, and similarly for our AR4 and AR1 models. So we see that there's a trade-off. The AR1 obviously doesn't fit the data very well, but it has the advantage of being really simple and therefore not prone to overfitting. On the other end of the spectrum, we have the AR10, which fits the data pretty well if you look at the graph. But it's using so many parameters that it might be really prone to overfitting. So we have to strike a balance. And the last number we need to care about is the number of samples that are used in fitting, which we're going to call n. So this ends up being important in BIC, but not AIC. So now let's go ahead and look at the mathematical forms of AIC and BIC and talk about why they make sense. So the mathematical form for AIC is 2k minus 2l. So let me scroll up so everything's in view. So this is basically saying 2 times the number of parameters used in the model minus 2 times the log likelihood. And we would like to make our AIC as small as possible. So we're going to pick the model that has the lowest AIC. Why is that a good idea? If we pick a model with a low AIC, that means that we're picking a model with a low k, or low number of parameters, which is good. We want to keep the model as simple as possible. But we also need to make sure that the model has a high L. And the reason it has a high L is because there's a negative sign here. So the story that AIC is telling is that I want a model that fits the data well, which means that L is high, the log likelihood is high. But I also want that model to have relatively few parameters k. And if you can find me a model that strikes a balance, then that's going to be the model I choose. That's the story that AIC is telling. Now BIC looks almost the same, and in fact, let me actually switch the order of something here so that it's a little bit easier to match these guys up. So BIC is natural log of n, k, minus 2l. So before I talk about BIC by itself, let's look at it with AIC. This minus 2l is common between these two, so it's the same. This k here is common. The only difference mathematically between AIC and BIC is this coefficient in front of k. In AIC, it's just the number 2, but in BIC, it's a little bit more interesting. It's the natural log of the number of samples that I used in fitting the model. So BIC takes also the number of samples used in training into account. So since we're going to pick the model with the lowest BIC, to make BIC as small as possible, the story goes like this. It's very similar to before. We say that we want a model that fits the data really well, so L is high. We want a model that uses relatively few parameters, so K is low. But the third part of the story that wasn't present in AIC is that we also want to pick a model that was trained on the fewest number of samples n. It turns out that for us, that doesn't really make a difference because all of our models were trained on the same number of samples. But you can imagine cases where you have two models who have the exact same number of parameters and who have the same log likelihood, so the AICs would be the same, but one of these models is trained on 1,000 samples versus the other trained on 1,000,000 samples. So in that case, BIC would prefer the model that's trained on 1,000 samples. So basically the story is that I would like to pick the model that fits the data the best, that's this minus 2L, that has relatively few parameters, that's this K, and also does so using the fewest data points, so that's this natural log of n. So there are, of course, theoretical differences between AIC and BIC, but this video is more about how do you interpret them in terms of their mathematical forms. So the last part of this video is actually getting the AIC and BIC, and it couldn't be simpler, because the nice part is we don't actually have to write any of the code to compute these formulas. AIC and BIC are literally just values that are stored within our fitted model objects, which is great. So in order to get the AIC or BIC from one of your fitted models, you just call .AIC, or you just call .BIC, so that's really nice. And we print out the AICs for our 4 models, and we're going to pick the one that has the lowest AIC if we're choosing to use AIC criteria, and we see that would be the AR6. So again, the story, just to drive the point home, is saying that the AR6 model is able to fit the data best and strike a balance between that fit and the number of parameters that were used. So the AR10, although it does fit the data better, those 4 extra parameters aren't worth it in terms of AIC. And if we scroll down to BIC, we actually get the exact same story. We see that the lowest BIC is achieved again with AR6, and the interpretation is pretty much the same. So based on both of these criteria, we would pick the AR6 model. So that's it, you guys. That's how you would take a time series, fit a bunch of different candidate models to it, and then use either the AIC or BIC criteria, who have these mathematical forms, in order to make a robust decision about which of these models you're going to use going forward. So any questions at all, please leave them in the comments below. Please like and subscribe for more videos just like this, and I'll see you next time.